All right, next we're going to be looking at trig, and so we're going to start off talking about angles and arcs of circles, specifically relating to radians and degrees and finding all sorts of things with that. So first, there are two ways to measure angles. And you should have worked with both of them before. The first is using degrees. So in degrees, we would start here. This is standard position. And we go counterclockwise around the circle. And when we reach a full circle, that's going to be 360 degrees. So this here is degrees. Technically, if you're writing an answer in degrees, you always need to have the little degree symbol up here. If you don't have it, then your answer is technically in radians. In radians, we're going to start in the same spot, go around in a full circle, but this time a full circle is 2 pi. When we're talking about radians, we don't have to put a little symbol. The lack of the symbol tells us that we're talking about radians. So what we have here is that 360 degrees equals 2 pi radians. I'm going to write the word radians, technically you don't have to. So if I want to know what pi equals, I can just divide both sides of that equation by 2, and I get 180 degrees equals pi. So from that we get two different ratios that we work with. The first ratio is 180 degrees over pi. And this equals 1 because they're both talking about half a circle. So half a circle over half a circle is 1. The other ratio we talk about is pi over 180 degrees. This also equals 1. And we use these 1s to convert between the two forms. So if I want to convert from degrees to radians or radians to degrees, I'm going to use this. So for our first example, let's say we want to write 14 pi fifths in degrees. So we're going to choose one of the two ratios. I want the pi to cancel out because degrees are not in terms of pi. So when I consider the ratio that I want to use, if I have pi on the top of my fraction currently, then I want to multiply this by the 1 that has pi in the bottom. So I'm going to use the ratio 180 degrees over pi. Now right away you'll notice the pi's cancel out, those are done. So in my calculator I'm just going to do 14 fifths multiplied by 180 degrees. And when you multiply that in your calculator you get that this is 504 degrees. Next example, we're going to write 42 degrees in radians. So in this problem, if I was to write this like a fraction, I can put it over 1. You don't really have to write it that way if you don't want to. And this time I want to choose the one that has the degree on the bottom so that my little degree symbol will cancel. That's my goal. So I'm going to multiply it by pi over 180 degrees, and my 2 degrees are canceling there. And in my calculator, we always want these answers in terms of pi, so we don't want to plug pi into the calculator because that would give us a decimal. So in my calculator, I'm just going to plug in 42 divided by 180. I'm going to take that answer and turn it into a fraction. So the fraction there is 7/30ths. So in radians, this would be 7 pi 30ths. All right, next we're going to talk about drawing angles. So when you draw an angle, you always start with this side right here. This is called the initial side. And then if your angle is positive, you're going to draw it up like this. So this would be a positive angle. And then this other side here is called the terminal side. Or if you have a negative angle, we'd have the initial side, and then the terminal side would be the other direction. So here's our initial, here's our terminal. And we draw these on a coordinate axis. So over here, if we're talking about degrees, this would be 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then all the way back to 360. And we'd say this is the first quadrant, second quadrant, third quadrant, fourth quadrant. Or if you're talking about radians, this would be 0 radians, pi halves radians, pi radians, 3 pi halves radians, and 2 pi radians for a complete circle. And again, we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Now, one of my pet peeves, and I know the other pre-calc teacher has the same pet peeve, is when students name the quadrants using regular numbers instead of Roman numerals. It is proper in math to use Roman numerals for these. So when you're talking about quadrant 3, I don't want to see you write the number 3. I want to see you write the Roman numeral 3. All right, so as far as drawing goes, here's our first example. We're going to draw 105 degrees from standard position. So standard position is what I just drew for you. So here, from here to here would be 90 degrees. We want to go a little bit further than that to get 105, about 15 degrees more. And so from standard position, that would be 105 degrees right there. So that's how we draw the picture. If they wanted to know what quadrant that was in, I would say that that answer is in quadrant 2. Again, using Roman numerals there. Let's say they want us to draw negative 3 pi eighths from standard position. You can draw this from radians if you want. That is just not the way my brain works. So whenever I see a problem in radians, I'll usually convert it to degrees first so that I can draw it more easily. So negative 3 pi eighths, I'm going to multiply by 180 over pi. And the pi's cancel. So negative 3 eighths multiplied by pi is negative 67.5 degrees. So I know that that's the angle that I'm drawing. And then I'll go ahead and draw it. Since this is negative, it means it goes down. If I went the entire quadrant, that'd be 90, so I'm going to go a little bit less than the entire quadrant. And so that's a negative 67.5 degree angle, and this here would be considered quadrant 4. All right, and last we're going to talk about arc length and sector area. So arc length is how long of an arc you're using. So let's go ahead and draw a circle to start. That would actually be helpful. So let's say this is the piece of the circle that we're looking at right here. Let's say that the radius is 5 inches. And let's say that this whole piece right here is 162 degrees. So if I'm trying to find the arc length, then I'm looking for this piece right here. So I'm looking basically for just a piece of the outside of the circle. And the way that you can think of this is you're taking basically the percentage of the circle or the part of the circle that you're looking at. So for this one, it's part of the outside of the circle, so I want to look at the percentage of the circumference of the circle that we're looking at. So the circumference of a circle is 2 times pi times r. So if I wanted to know what the circumference of this whole circle was, I would do 2 times pi times 5. But I don't want the whole circle, I just want 162 degrees out of the entire circle, which is 360. So I'm going to say the percentage of this that I want is 162 out of 360. Now typically when you multiply this out, you're usually going to leave it in terms of pi to be proper. These problems make more sense in a story problem, and so we'll practice plugging them in the calculator as well. So this is 9 pi halves inches. In a story problem, pi doesn't quite make sense, and so we're going to plug this into the calculator and say that this is approximately 14.137 inches. So that is arc length. That's how you find that. The other thing we'll find is sector area. So the sector area is saying, what is this whole area right in here? And we're going to find it in a similar fashion, but now we're talking about area. So we have to remember that area is pi r squared. So the area of the entire circle would have been pi times 5 squared but we're not talking about the entire circle, we're talking about just that percentage of it. And the piece of it that we're talking about is 162 degrees out of 360 degrees. So if I plug that into my calculator, leaving pi in the answer, I would get 45 pi fourths inches squared. But since this makes more sense in the context of a story, if you say like, oh, what's the area of that sector? And someone's like 45 pi fourths, you're like, I don't know what that is. So normally we'll plug these in and find the approximate answer. And here it would be 35.343 inches squared.